Hello everyone and welcome to our last video in combinatorial analysis. So after this video, we'll be doing a bunch of practice problems on this section, and after that we'll actually be getting into probability. This video specifically is very tedious because there's a lot of material and it's the last section in combinatorial analysis, and I know you guys want to get through it already because counting the number of outcomes is getting a lot. But you'll get through it, and just know that this section isn't as important as the first two. However, it utilizes everything we've learned, and there will be times when we'll be using the binomial theorem and everything else we'll be learning today to help us out with probability. Even though it might seem a little vague and abstract, it's all very useful, and just try to pay attention and try to work through the examples I do here. And then in the next video, we'll be doing a bunch more examples from lesson 1 all the way to lesson 3, which is this lesson. But let's just get straight to it. So the binomial theorem is up first. So the first thing you should know before we actually state the theorem is this. N choose R is known as a binomial coefficient. Right? So coefficient usually means a number that's in front of a variable, right? So like 3x squared, the 3 is the coefficient. And binomial just means, well, you'll see right now. It's known as the binomial coefficient because, I can't spell, because of its use in the binomial theorem, which I'll state right now, in the binomial theorem. Okay. And this is what the binomial theorem says. If you have a sum of two numbers, x and y, and it's raised to some power n, where n is, in our case, let's just say n is a natural number, so it could be to the power of 0, 1, 2, 3, 4, etc. Raised to the power of n. So this equals the sum. If you haven't seen this symbol before, I'll explain this shortly. But this means sum. The sum, as k starts at 0 and goes all the way to n, of n choose k. So there's your binomial coefficient, and it's in front of x to the k times y to the n minus k. This is true, and I'll list out the proof in the description. So if you're curious to see why this is true, you can see the proof in the description, and it's in PDF format. So proof is in the description if you want to see it. I'm not going to write the proof, it's kind of boring. Okay, so if this is the first time you're seeing this symbol, if you've taken calculus, you probably remember doing series, but I'll just restate it. So recall that the symbol sigma, I believe, in Greek, sigma? No, it's not sigma. I forgot what it's called in Greek, but this symbol in mathematics usually denotes a summation. So for example, the sum of 1 plus 2 plus 3 plus 4 plus 5 can be rewritten using the symbol as follows. you draw the symbol, and on the bottom, you put in your first index. Where does your sum start at? Well, it starts at 1, and let's call it k. So k starts at 1, right? Because our sum starts at 1. So you put it here on the bottom. But then you have to tell yourself, okay, where do I end? Do I end at 4, 6, or 5? 5, obviously, for this case. So all you have to do is just put the 5 there. Great, now you know where you start, and you know where you finish. So this means that, and this means that. So those are equivalent terms. So let's just do some examples just to get familiar with this. I'm not sure, of your guys' background, so I just want to make sure that you understand this, so we can actually talk about the binomial theorem. Okay, so let's do just 2 short examples. The sum from k starts at 3 and ends at 10. So try this out on your own. Okay, so I know k starts at 3, and the summation increments by 1. So I start at 3 and then I add 1 to it, which is 4, plus 5, plus 6, plus 7, plus 8, plus 9, and then I end at 10. So this entire sum can be just rewritten as this. It's just a lot better to write this usually because it's cleaner and it's nicer to look at. And let's just try another example using the binomial coefficient, just so we could get used to writing that out. So the sum when k starts at 1 and ends at 5 of n choose k. So try this out on your own. And this is more important than this because we'll be actually using that here. But in this case, k starts at 1. Now wait, what is n? Well, n denotes anything that is on top of the symbol, okay? Because you end at 5. However, the n is fixed, okay? You end at 5, but the n is your 5. So 5 is always there on top, but k changes. So first it's 1. Okay, I got my first term, my first binomial coefficient. But then I have to add all the increments of k. Okay, I still have a 5 on top because the n doesn't change. Then I add 1 to k, so I'll have 2 here. 5 choose 2, plus 5 choose 3, plus 5 choose 4. But I'm not done because k has to go all the way to 5. Plus 5 choose 5, and that's your answer. I mean, you could compute this, but that's not what I want you to take away from this. I just want you guys to understand how to use the summation. Okay, so now that we got this out of the way, let's actually start using the binomial theorem to see why it could be useful. So I want to erase this. Do I want to erase this? No, I don't. So let's do it here. Okay, so using the binomial theorem, let's expand x plus y to the third. So most of you can do this using the FOIL method, just by distributing the x to the y and so on. But I want you guys to actually use the binomial theorem to show you that you don't even have to use the FOIL method. You could actually use this, and you're probably thinking, why would I want to do that if it's easy to FOIL? Well, it turns out when the power of n goes higher, this gets way easier than using the FOILing method that we're also used to. Okay, so let's expand it using this definition. Okay, so I have a 3 for my n. So that means x plus y to the 3. So my n equals 3. So remember that. So I have a sum that it always starts from 0. K always starts from 0 in the binomial theorem. K equals 0, unless you're told otherwise. And then I end at my n. In this case, my n is 3. So I have a 3 on top. And then you work through this. So first, I'm not going to spread out the sum. I'm just going to write it with the symbol. So my n is 3. So you can write the 3 because it doesn't change, right? The 3 of the n always stays the same in the binomial coefficient. But your k changes. So I'm going to leave it as k. And then you have x to the power of k. So I'm going to leave it as k. Y to the n, which is 3, minus k. Okay, we could rewrite this now, right? Just as we did here, just a little bit more complicated, but not so much. Let's just start. So k starts at 0. So let's just start from 0. You have the 3 on top, and k starts at 0. You still have the x there to the kth power, in this case k is 0. Y to the 3 minus 0, which is 3. Now plus, right? Because k has to reach the 3. You're not done yet. Okay, so plus, now my second binomial coefficient where k equals 1, x to the 1, and y to the 3 minus 1, which is 2, plus 3, choose 2, x squared, and we have y to the first. And finally, our k finally reaches the n, which is 3. So we have a 3 here, and then a 3 here. 3 choose 3, and then x cubed and y to the 0. If you compute all the binomial coefficients, what you end up with is y cubed plus 3xy squared plus 3x squared y plus x cubed. And just for fun, try the FOIL method and see if you come up with the same answer. I mean, you will, but just for fun, just to actually prove it to yourself that it's true for this case. Again, if you want to see the proof for this theorem, it's in the description. I'll link it down below. Okay, so let's just do one more. This one is pretty much the same problem. I'm just going to use a bit different notation so you guys get used to it, because I don't know if you're looking at the same textbook as I am. I just want you guys to see different notation just to get used to it if we're dealing with different variables. So let's say I have x1 plus x2, and this is squared. It's literally the same thing except n is actually just 2, and these are just different variables. I could have easily written x and y, but I just want you guys to get used to different notation. So this is just x1 and this is just x2. They're just some variables, or some numbers actually, that can change. Okay, so try this out on your own, but I'll get straight to it. So I always like to write out the summation with the symbol first, just to see what I'm working with, and then I expand it. Okay, so you always start with the summation symbol. K always starts from 0, and you work your way till 2, right? In this case, n equals 2, right? Because the n denotes here. So 2, choose k, x1 to the kth power, and we have x2 to the 2 minus k. Again, I'm writing it as x1 and x2 with the indexes here, just so you guys can get used to it and not be scared of looking at weird variables like this instead of just x and y, because it turns out we sort of run out of alphabets, the letters in the alphabet, so we just like to denote the same letter with different indexes, so 1, 2, 3, and so on. So it's literally the same problem, just different variables. Okay, so we're ready to expand this. So this equals, well, I start with my binomial coefficient. 2 always stays there. My k is changing. It starts at 0. So I put a 0. X1 to the 0. And x2 to the 2 minus 0, which is 2. Plus, remember, the k always has to finalize at the end. Okay, so 2, choose 1. X1 to the k, which is 1 here, times x2 to the 2 minus 1 is 1. Okay, and this is the last term because my k finally reached the n, which is 2 in this case. So 2, choose 2. x1 to the 0th power and x2 squared. No, wait, sorry. The other way around. Right? Yeah, x1 squared because it's to the kth, and this is 0 because 2 minus 2 is 0. And what you can end up getting is, what is this, x2 squared plus 2x1 x2, right, because they're to the first power, and plus x1 squared. And we're done. Again, try the FOIL method and see if you get the same result. And you should. Okay, so that basically covered the binomial theorem, except, we're going to be building more upon it. So, don't forget about it. It's still going to come up. It's just that we don't have that many examples just yet. Okay, so let me erase this and we'll get to our next topic. So remember, when you think of binomial theorem, think of the coefficients, the binomial coefficients, and you're doing a summation to expand the sum of two numbers to some power. And that power is usually a natural number. I mean, that's what we'll mostly be dealing with. Okay. So our next topic in this video is multinomial coefficients. And if these were binomial coefficients, then try to think of what might be a multinomial coefficient, right? Multiple coefficients. Well, before we actually look at the notation, let's see why we're even interested in knowing what a multinomial coefficient is. So here's the proposal. This is why we're interested in. So we have a set of n distinct items. So, n distinct items, think of the English alphabet. You have the letters A, B, C, all the way to Z. So let's say, think of the English alphabet. So in this case, if we have n distinct items, when we think of the English alphabet, we have 26 distinct items, right? 26 distinct letters, A through Z. So n in this case equals 26. This is just a way to sort of, get away from the abstraction so you guys understand what I'm talking about. So you have a set of n distinct items. Think of the English alphabet where n equals 26 because we have 26 letters. And these n distinct items are to be divided into r distinct groups, like a combination, but these groups are distinct in a way where each group is of groups of sizes n1, n2, all the way to your last group size. So, and where the sum of the sizes of your groups, so the sum has to equal the total number of items. So you can't have as many groups as you want. You have to have as many number of groups as this allows it to. So the size of each group has to add to 26. And each group has to be distinct, right? You can't have A, B, C, and C, B, A. Those are the same group. So remember, this is just, you can rewrite this using the summation symbol, right? Where you have a sum of n, where the index is I starts at 1, and it ends at r. Oh, sorry. I mean, it is 26 in this example, but in general it's n. So this equals n. So for example, if we have the English alphabet, for example, one group could be A, B, C, and the size of this group can be n1, which equals 3, right? There's 3 letters, that's the size of this group. Or, we have a group D, E, K, and Z. Oh, this is just maybe n2, doesn't really matter. Oh, but the size of it is 4. And once you reach all your groups, they have to add up to the total number of distinct items you actually have. So you can't have as many groups as you want. So this is the whole big deal. This is the underlying question. We want to know, remember this whole section is about counting, right? So we want to know how many different divisions are possible. So how many different divisions of n items into our distinct groups are possible? Where the sum has to equal n. So think of the English letters. Group 1 could be A, B, C, n1 equals 3. Group 2 could be Z, Q, R, T, W, and the size of that is 5. And then you keep creating distinct groups until the size of each group added together equals 26. That's just one possible division, right? You could keep going on and see how many, and we want to know how many different divisions are possible. Given that we have a certain number of distinct items, we want to separate them into our distinct groups in such a way where the size of each group added together actually equals the size of the original number of items you started with. Well, how many divisions are possible of n distinct items into our distinct groups given this? Well, let's try this. Let's put it in terms of experiments, okay? So, experiment number 1. Let's think about this. Experiment number 1. Well, for our first group, we have to choose the number of items in that group from the total number we have, right? To start my first group, let's say from the 26 letters in my English alphabet, I have to pick out some number of letters to start my first group. Let's say from the 26 letters, I choose A, B, and C. For my first group, the size is 3. So I have to first choose my first group. So we have to first choose a certain number of items, say n1, right? n1 is just some number of items from the total n to get our first group. Okay, now how can we do this? Well, we have to choose n1 items from n. We did this in the last video. You guys should be able to do it. How do you choose some number of items from a total number of items? Well, we have a total number of n items, so n goes on top because remember, in this case, r equals n1 because you're choosing a certain number of items from the total. So this inherently has to be either less or equal to the total. So n1 goes on the bottom. You're choosing n1 from n. That's how many possible this is the number of items. This is the number of ways you could make your first group. Number of ways to make first group. Okay. Great. Well, experiment number 2. Well, once we have chosen a certain number of items from the n, right? We chose n1 from the n. Let's say I chose the letters A, B, and R. I can't choose those letters to be in my second group anymore because this has to hold. So, I can't choose any of those n1 letters I chose for my second experiment. So we're not working with n anymore. We're working with the rest minus this. So n minus n1. So once we have chosen n1 items, right, a certain number of items, we now have a total of not n items to work with, but actually n minus n1, right? Because I can't choose any of those letters again. I have to choose the rest of the letters. So n minus n1 items. So that's the total now for experiment 2. And from this, we choose n2, right? A certain number of items from this. So let's call it n2. We choose n2 items. So how do you choose n2 items from the rest of the items that we have now? Well, we now have a total of n1 items, so that goes on top. And we're choosing n2 items from this. So n2 goes on the bottom. And you can continue this pattern until you reach your last experiment, your last group. So let's call that experiment number R, because it's our last group. Experiment number R, we would be essentially choosing NR items, right? The last number of items we can choose. NR items from, well, we don't have n anymore. We don't have n minus n1 anymore. We have, well, what do we have? We have n minus n1 minus n2 minus n3 minus all the way until you reach, so n minus n1 minus n2 minus n3 minus blah 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 minus n r to the minus 1, r minus 1. Because if you notice, here we chose, we subtracted n1 and we chose n2. Here we're choosing nr and we go all the way to n to the r of r minus 1. Right, because this is the last number of items, but you've already picked all these in the previous experiments all the way up that are here. So you have to subtract all of this, and this is now your total number of items. And you're choosing nr items from this entire new list. Okay, so now my new total is this. So I'll just sort of rewrite it, sorry. N minus n1 minus all the way until you subtract off the few last items. And you're choosing nr items from this new total. Great. And now we found the number of outcomes for each experiment, right? Even though I haven't written experiment 3 or 4 or whatever, you guys can see the pattern. So, by the basic or the general version of the basic principle of counting, if you have a certain number of experiments and each experiment has a certain number of outcomes, you have to multiply the outcomes together to get the total number of outcomes possible. So, by the basic principle of counting, we have this times n minus n1 minus n2, choose n3, times blah blah blah, until you finally reach this. So what we have is n, choose n1, times n minus n1, choose n2, times blah 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 blah, all the way until you reach n minus n1 minus n2 minus blah 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 minus n to the r minus 1, choose nr. You're multiplying all these terms together to find the total number of outcomes. And we're done technically, we're done. But we want to, this is not a clean answer. We want to sort of use algebra to divide things out if we can. So, I mean, we can't work with this, right? We have to understand what does n choose n1 mean. Well, if you think back to last video, it's just the definition, right? So let's unravel what each of these terms mean. N choose n1, oh, that's just n factorial, times n minus, remember, over here you have n minus r. R in this case is n1. So you have n minus n1 factorial times n1 factorial, right? Because you have r factorial. Okay. Times this term. Oh, that's just, well, the top is n minus n1 factorial over this minus that, n minus n1 minus n2 factorial to the n times n2 factorial times all the way until you reach, so this entire thing to the factorial, right? So n minus n1 minus nr minus 1 factorial over this minus this factorial. Now, this minus that is actually 0. It's 0 because look at this. So over here, what you're actually doing is you're adding, so what comes before nr? Well, you have an nr minus 1, right? You have an n to r minus 1 before the nr term. So what do you have here? You have n minus this, minus that, minus n3, minus this. And then you're subtracting off this. So technically what you're doing is n minus this entire thing. Well, this is n, so n minus this is 0. So you get 0, and remember it's to the factorial. Right? Why were you even subtracting them? Remember, you have to subtract n minus r. In this case, n is this entire thing, right here. And the r is the nr. Okay, so that's 0, and then we have the factorial. And times the r factorial. In this case, r is nr. So nr factorial. And you're probably wondering, wait, this looks even worse. But blink and you miss it. Oh, I could cancel these. And if you actually write out everything, you'll notice you will cancel this, and there's going to be another n minus n1 minus n2 there. And you'll end up canceling this as well. So, if you don't believe me, just write it out yourself. I actually encourage you to. So every term here in the denominator and numerator will continually cancel out. 0 factorial is just 1, right? That's how it's defined to be. Oops. So you just have a 1 there. I don't even know why I'm writing it. Okay, so in the numerator, well, you're just left with n factorial, right? Because everything else gets canceled out. Okay. And then in the denominator, well, this gets canceled out, so you're left with n1 factorial times. This gets canceled out, so you're left with n2 factorial. And if you repeat the pattern, you'll finally end up at times nr factorial. And we're done. What is that? So this is the total number of divisions that are possible. And that's our answer. That's it. You know, we could have stopped here and that would have been fine, but this is much cleaner. And if you remember back to permutations, this is actually the same definition we used when we had certain number of objects that were indistinguishable from each other. And at first you had this many linear arrangements of the n items, but then you had to divide out by the letters or objects that were the same to each other. So try to think of why that is. If you're not sure, I'll give you a hint in the comments, and if you're still not sure, I'll let you know. But it's you know, it just takes up too much time to explain in the video, so I'm not going to. Okay, so you know, we had the 0 factorial here again. Where did the 0 come from? Let's work here, right? So n, and I'm going to subtract all from here. So n minus n1 minus n2 minus n3 minus all the way, and then I'm subtracting off, let's say, minus nr minus 1, and this then equals nr, right? Because I subtracted everything except nr. But in this problem, I have to subtract the nr, right? So I have to subtract that off from n. Oh, I'm left with 0. And that's where the 0 came from. And then you have the factorial, because that's in the definition of a combination, or the binomial coefficient definition. And that's it. Okay, so that was a lot of theory. And you know, if this confused you and if it's too much abstraction, I know there's no numbers in here except the 0. But try to think of the English alphabet, try to think of the letters, and see if you could fill out this on your own. We'll be doing a lot of examples with numbers right now, so be relieved. But if you guys didn't understand this, please leave down a comment and I'll try to get back to you. But this is why we care about multinomial coefficients. We have this nice way to represent the total number of possible divisions of n distinct items, n distinguishable items. And we want to divide them into r distinct groups in such a way that when you add all those sizes of each group, you end up with the total number of items you had. Okay, so we'll start our examples right now. Okay, so here's our example. A school in a small city consists of 10 teachers. If 5 of the teachers teach English, 2 of them teach math, and 3 teach biology, we want to know how many different divisions of those 10 teachers are possible. When you hear divisions, always think of multinomial coefficients, okay? Everything we just did in theory, think of multinomial coefficients when you hear divisions. So, okay, so you think of multinomial coefficients. What do we have in multinomial coefficients? We have an n, right? We need to know what our r is. N is the total number of distinct items. R is the total number of distinct groups. And we have to understand how many terms we have for n1 and n2 and nr. That's sum to n. So let me write that down. So we know that this is a multinomial coefficient problem because of the word divisions, okay? And we want to know what is n first, right? What is n? Well, what is n? N is the total number of distinct items. N has to be 10. We have 10 distinct teachers, right? Okay. So n equals 10. We have 10 different teachers. Next, we want to know how many different groups, distinct groups are there. What is R, right? Which denotes the number of distinct groups. Well, we have three subjects, right? We have English, math, and biology, and each of those groups or each of those subjects has a certain number of teachers. Well, okay, let's not worry about the number of teachers in the group, but how many groups do we have? We have 1, we have 2, and then we have 3. So R equals 3 distinct groups, right? English, math, and biology are 3 distinct groups, 3 distinct subjects. And finally, we want to know what is N1, N2, and R, and how many of them do we have? You have as many N1s, N2s, and Rs as many groups as you have. So in this case, I'll have N1, I'll have an N2, and I'll have an N3, and no more than that, and no less. Okay? You'll have the same number of sizes for each group as the number of groups you have. And that should make sense, right? If you have 3 groups, you should have only 3 sizes, where the 3 sizes is respected to each group. So, N1. So these could be in any order you want. I just go in order of the question. N1 will be the size of my first group. Well, my first group is English. How many teachers teach English? Oh, 5. So the size of the number of items, number of teachers in that group, in that subject, is 5. So I'll denote N1 as 5. Okay, N2 is the number of items in my second group, which is math. I have 2 items or 2 teachers, so N2 equals 2. And then finally for my last group, which is biology, I have 3 items in there, or 3 teachers. So that's 3. And notice, so I'll write it here. Notice N1 plus N2 plus N3 equals 5 plus 2 plus 3. 5 plus 2 plus 3, which is 10, right? And that should make sense. You have to get 10. If you don't get 10, you probably did something wrong. So make sure to check this after you labeled all your variables. Well, we have all our variables to do the multinomial coefficient because we have this definition, right? We have n, total number of distinct items, choosing your n1s, n2s, and n3s in this case. We don't have any more. Okay, you only go up to 3 groups. So you have 3 different sizes. Remember, these denote the number of items in each group. Okay, so in this case, our n is 10, right? You're choosing for your first group 5. Then for your second group, you're choosing 2. And then you're choosing 3. And this is actually how we denote the multinomial coefficient. Did I write it down actually for you guys? No, I didn't. Okay, sorry. So let me just backtrack. I did not write notation. So the multinomial coefficient, so what we had here, n factorial over n1 factorial times n2 factorial times all the way to nr factorial. Remember, this is what we had for the total number of possible divisions. Well, instead of writing this all the time, we just like to represent it as n choose all these respective sizes. Kind of like a binomial coefficient, right? Except this time we have multiple variables on the bottom, except, oh, why do I keep writing 3? So this is what it means. Sorry, I skipped over this, but now that you have the notation, 10, choose 5, choose 2, choose 3 is just 10 factorial over 5 factorial times 2 factorial times 3 factorial, and you're done. And this turns out to equal 2,520 possible divisions. And we're done. That is the answer. Now, I want to show you guys another way of doing this problem. It's very short. It actually involves solving it in a way we actually first looked at multinomial coefficients with the experiments. So, experiment number 1 experiment number 1. Remember, you're choosing n1 from n first, right? You have to choose your first group from the n items you have. So choosing a total number of n1 items. So choosing n1 from n. Well, in this case, n1 is 5, so 5 from 10, right? Oh, that's just 10 choose 5. Right, 10 choose 5. Experiment 2. Well, we have to choose n2 items, right, for our next group, choosing n2 from, well, we no longer have n, remember? Because you already chose n1 from n, so you have to subtract off n1 from n, so now you have a total of n minus n1 items. Okay, so you're still choosing n2, which is 2, from, and it's no longer 10, it's 10 minus 5, which is 5. So you're choosing two distinct items from the 5 items that you now have. Oh, but this is just 5 choose 2. And then finally, experiment 3, which is our last experiment because we only have 3 groups. You're choosing n3 from your new total number of items, which is n minus n1 minus n2, right? If you go back to your notes, when we first introduced multinomial coefficients, this is actually how we started, and then we came to terms with this. Now we find that this is actually easier, but I just want to show you guys that you could do it in this way too. So now you're choosing n3, which is 3, from n minus n1 minus n2 is 10 minus 5 minus 2, which is 3. And for your last experiment, you'll always have n choose n, which is 3 choose 3 in this case. So by the basic principle of counting, you have to multiply all these together. So you'll have 10 choose 5 times 5 choose 2 times 3 choose 3. And if you punch this in your calculator, you will get the same exact number, which you should. So that's just another way to solve it. Personally, if you're, during the test or if you have a time constraint, definitely do this. If you just want to, work it out this way, that's fine too. I just prefer this way because it looks a lot more intuitive to me. And that's it. Yeah, sorry about not listening to the notation earlier. So this means that and that means that. Just like we had our regular binomial coefficient, n choose r meant n factorial over n minus r factorial times r factorial. In this case, this means n factorial over all this product, and that's it. So in this case, we only had 3 groups, so you have only 3 numbers here. So the top is 10, you have choose 5, you choose 2, and you choose 3, and this means that. And then you just solve this, and you get this number. Or you could do it that way. Okay, so that pretty much introduced us to a nice easy example for multinomial coefficients. These next 2 examples are a bit tricky because they look the same, but one is a little tricky. So we'll do the easiest one first and then we'll move on to the harder one. Okay, so let's start both of these examples. So if you're reading both of these examples at first glance, they look very similar, but we'll see shortly how they differ. And this is the importance of the last lesson we did on combinations. So of course try them on your own and see if you come up with the answer. If you don't, that's fine. Just once you see my solution, make sure you understand where you went wrong. Okay, so let's look at this first example right here. Well, is this a multinomial coefficient problem? How do I know? Always try to look for the word division. If you're trying to divide stuff into groups. Here I see divisions and here I see divisions, so I think of multinomial coefficients. Okay, And I think of combinations as well, right? Because we're using, this comes from a combination, because it's a group, distinct group. So I have to write down what my n is, what my r is, and what are my n1s, n2s, and so on. Well, notice that for this problem, notice that my n is 10, right? Because this is 10 distinct children. Even if even if two of them are twins, they're still distinct. So 10 distinct children. Remember, your n is the number of distinct items. Your r is the number of distinct groups. Well, your r has to be 2 because you have an A team that plays in one league and you have a B team. Those are two different teams. Those are two different groups, two distinct groups. So you have two distinct groups. So that's why r equals 2. Okay. And how many n1s do you have? Well, you have how many n1s, n2s, n3s, and so on do you have? You always have the same number of groups you have, right? So you have an n1 and you have an n2 and no more and no less. So your n1, well, your first group, well, they each have 5 children in there, right? So 5 items. So group 1 has 5, and group 2, which is my n2, also equals 5, because each group has 5 children. That's the number of items in each group. Okay, and that's all we need to solve the problem, right? Because look up here, I filled everything out I needed. R just lets me know how many n1s, n2s, n3s I need. So, knowing this, I should have, on top I have my n. So n is 10. And I have only 2 numbers here. So my first n1 is 5. And then I kind of drew this too big actually. So I should have a 5 over here and another 5 over here, and I have a 10 right there. 10, choose 5, choose 5. Oh, but this just means that. So on top I should have a 10 factorial. And then I have only these two, right? Because I only have 2 groups. So I just have that. So I have 5 factorial times 5 factorial. And this actually ends up being 252 possible divisions. And that answers the first question. Okay, so the second question. In order to play a game of football, 10 children divide themselves into 2 teams of 5 each. How many different divisions are possible? You know, when you read that question, you're like, wait, how is this different from this question? Here I have 2 teams. Here I have 2 teams. I have 10 children here. I have 10 children there, and each team has 5 children. So why can't I just use the same number here? Why isn't it 252? Well, the problem is these 2 teams, even though it's hard to see by the question itself, are inherently indistinguishable. I cannot tell the teams apart because they're not an A team or a B team. They're not playing in one league or the other. They are just 2 teams. And it doesn't matter how, if I'm talking about with the other team or my team or that team. So, if I rearrange the 2 teams, it's the same group. So this is actually different than this because the 2 teams are indistinguishable from each other, unlike here. Here I specifically have an A team and I specifically have a B team. I can tell those 2 apart for sure. One's A team and one's the B team. This problem, I just have 2 teams. I don't know which one is which. So to me, they are indistinguishable. Because they're indistinguishable, we technically should have less divisions. So let's work through it. So let's move here. So note this problem is slightly different than that. Well, our n is actually still 10. Okay, that stays the same because we still have 10 distinct children. So that stays the same. R is the total number of groups, distinct groups. 2, we have 2 groups, but these groups are no longer distinct. Are no longer, distinct. So we'll come back to this. And we still have 2 items. We still have 5 items in each group, right? So n1 equals 5 and n2 still equals 5. Okay. Now, if we were to solve that problem like this, well, you would still have 10 choose 5, and then you would come up with 10 factorial over 5 factorial times 5 factorial. But because the 2 groups, the order doesn't matter, we're actually overcounting, right? We're overcounting, and if you think back to our last video about combinations, when order doesn't matter, you have to divide out by the number of ways you can rearrange the 2 groups, okay? Because in this problem, these 2 teams are the same group. I cannot tell them apart. So it doesn't matter who I'm talking about, first or second. And I'm overcounting by the number of ways I can rearrange the 2 groups. How many ways can I rearrange 2 groups? Well, I have 2 spaces. My first space, I could pick any of the 2 groups. And then I only have 1 group to choose from in our second space. Oh, that's just 2, which is 2 factorial, right? 2 factorial is 2 because 2 factorial is just 2 times 1. So I'll just write it as 2 factorial. And what do we do with this number? Well, this is the number of ways I can rearrange the 2 groups, which is bad because they're indistinguishable. So I have to divide by that number to actually get the total number of actual divisions. So I have to take this and divide it by 2 factorial. So what I actually end up getting is 10 factorial over 5 factorial times 5 factorial. And when you divide by 2 factorial, it actually ends up in the denominator, right? Just simple algebra. And that is your new answer, which is exactly half. So 126 possible divisions. And notice, this is actually, using that notation, 10, choose 5, and choose 2. So you can just leave it like this if you want. Obviously, I think going to this first makes more sense because you're dividing by 2 factorial after you get this. But then you can just rewrite it as a multinomial coefficient notation, and it just looks nice. And that is the answer for the second problem. And notice how it's exactly half of this. And that should make sense, right? Because now the two teams are indistinguishable. So I'm dividing by the 2, which gives us the 126. So 252 divided by 2 will give you that 126. And that's it. That actually covers multinomial coefficients. We're actually going to come back to them very shortly after this next section. And this next section is going to seem very out of nowhere. Like, wait, what are we doing? And the only way I could actually, motivate this next topic is we'll just be using it for something that will be using multinomial coefficients. And it's actually very interesting and it's useful in some ways. So, if you get anything out of this next topic, just, believe me that it's interesting. At least I thought it was when I first learned it. So I'm gonna erase this for now. Yeah, so again, this next topic, it's, when I learned it, it was actually not required in my probability course, but I'm gonna cover it anyway because I think it's useful for the topic after this topic. So we're still gonna do it. Do you have to know this topic? No, but it's very useful to have in your arsenal, trust me. And again, it is interesting, I think it is. So sort of switch gears for a sec, okay? Because the motivation for this doesn't use anything we've learned, but the problems do. So the motivation is kind of new. But this topic is called the number of integer solutions to two equations. It's a big title. The number of integer solutions to equations. Okay. Alright. So here's the motivation. It will be useful to us. It'll be useful to find how many, we're still counting, right? So we're still on track. So it'll be useful to find how many distinct, distinct, non-negative, non-negative, and I'll talk about what that is in a second, non-negative and positive integer valued vectors. Integer valued vectors. And I'm not talking about the vectors you learned in calculus, so don't worry. I'll show you what that means. So vectors that are denoted as such. So x1, x2, and xr. So this is a vector such that x1 plus x2 plus blah 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 plus xr equals n. And that is our goal for this topic. We want to find a way to count the total number of vectors that have this outcome. Now, when I say vectors, I'm just talking about a list of numbers that satisfy this equation, okay? So, for example, first, let me talk about non-negative, distinct. Oh my god. What is that? Sorry about that. Distinct. Non-negative and positive integer. So what is non-negative integers? So just to refresh your memory if you've never seen it before, non-negative integers is the set of these numbers. So 0, 1, 2, 3, and so on. So non-negative just means, well, not negative numbers, right? Only the positive numbers plus 0. 0 isn't positive or negative. So non-negative are these integers. While positive integers is actually the set of 1, 2, 3, etc. So it's literally almost the same set, except non-negative integers have a 0 and positive integers do not have the 0. And the positive integer valued vectors and non-negative valued vectors. Well, this list has to have, if we're talking about non-negative integers, it has to have these numbers, only these. It can't have, pi or 1/2 or 4/5. It has to only have these numbers. So this list can only include these numbers if we're talking about non-negative. If we're talking about positive, it only can include these numbers. If that's still, so also this is known as the natural numbers, okay? So, don't worry about this. This just means that, and that just means that. This is the set of natural numbers. And this is the set of non-negative integers. Okay, so don't worry if you're still confused about all the, notation and the ambiguity. I think after this example, it'll become clear. So, for example, we want to know how many non-negative, so let's talk about non-negative first. How many non-negative valued vectors come up for this equation? x1 plus x2 equals 3. So I want to know how many lists of these numbers I can make so that the sum equals 3. Well, let's just try to write them down using logic. So, that's a horrible arrow. Let me just write it here. So pick values for x1 and x2 from this list, not this, because we're talking about non-negative first, from this list, such that when you add them together, you get 3. So, x1, well, let's pick 0 first, right? So I can pick 0. Well, if x1 is 0, then x2 must be 3, right? Because 3 plus 0 will give you 3. So that means if x1 is 0, x2 must be 3. Oh, this is my first non-negative valued vector, where x1 is 0 and x2 is 3. And in this case, it's just the ordered pair 0, 3. And that's it. That is a non-negative valued vector. Your first term is 0. Your second term is 3. If we had more terms, we would have had more numbers here. In this case, we just have 2 terms. That's why we have only 2 terms in our vector. Okay? A vector is just a list, not the vector you encountered in calculus 3 or linear algebra. But we're not done, right? I could come up with more from this list. What if x1 were 1? Well, if x1 is 1, x2 is 2, right? 2 plus 1 is 3. Then x2 must be 3. Okay, so I found another vector where the first term is 1 and my second term is 3. Perfect. But I'm not done. Oh, sorry. This is 2, not 3. That should be a 2. I still could keep going. Let's see. What if, well, x1 could be 3, and then x2 could be 0, right? So I just switch these. And notice this is different from that because my x1 changed and my x2 changed. And 3 plus 0 gives you 3. So this is my other vector, 3, 0, non-negative vector because I have a 0. And I think we have one more where I switch the 2 and the 1 here. So x1 can be 2 and then x2 can be 1. And this is my final and last vector where the sum of x1 plus x2 will give you 3 from this list only. So 2 and 1. 2, 1. And the question asks, well, how many vectors are possible for this equation? Oh, 1, 2, 3, 4. 4 vectors. 4 non-negative. Actually, non-negative vectors. Integer vectors, but that's implied already, right? We only can have integers. We can't have 1/2, we can't have -4, positive integers, or non-negative. We can't have -4, We can't have negatives, we can't have irrational numbers or fractions. We must have non-negative integers or positive integers for these types of problems to work. So we came up with 4. And we found how many distinct non-negative valued vectors? 4. And that's it. Okay. Don't want to say anything about this. No, not at the moment. Okay. So let's see. Do I have an example for this? Yes, I do. Okay. So, this, it's useful, and we actually, it's kind of annoying doing this by listing it out. We want a formula to sort of actually just count the number of outcomes, just as we've been doing, right? And if you remember back to lesson 1, when we were trying to find the number of outcomes of 2 experiments and we had to list them out, you saw how long it took. Now imagine if you had more terms here. This took not that long, but what if we had, 50 terms and you wanted to count the number of vectors you had? That would take a while. So we have something to help us out. If I could find it, that would be great. Oh, there we go. Found it. Okay. So I'm going to erase this. Okay. Erase this. So that was just us listing it out, right? We didn't have any nice formula to count the number of vectors. We actually just got them from writing what x1 is and what x2 is. So remember, the goal for this topic is to count the number of either non-negative integer valued vectors, which are just lists, or positive integer valued vectors. So we have the following propositions that will actually help us count the number of vectors that there are. So here's the first proposition. And proposition is just like a definition, but a little weaker than that. Proposition 1. Oh, right. So this is what I wanted to say. So we had, so going back to the last example, I think we had 0, 3, 3, 0, 1, 2, and 2, 1. And we had 4 non-negative integer valued vectors. If you wanted to answer it for only positive integer valued vectors, where the positive integer starts at 1 and not 0, well, just erase the list that has 0. And you come up with only 2 positive integer valued vectors rather than 4 non-negative. So if you want to know positive, I would actually suggest count the number of non-negative and then, well, if you're listing them, do the non-negative and then subtract off, or just list out the positive and that's it. Okay, so proposition 1 is for counting the positive integer valued vectors. And the way you do it is, there are n minus 1, choose r minus 1 distinct positive integer valued vectors. Right, so positive integer valued vectors do not include 0. They include the numbers 1, 2, 3, and so on. So positive integer valued vectors, x1, x2, xr, satisfying the following equation. So we wanted to satisfy x1 plus x2 plus all the way to your last variable or number, and it equals n. Okay, so we want it to satisfy this equation, so we could get out this list, right, this vector of these values that sum up to n when every term here is actually greater than 0, right? Because again, we're talking about positive first. Positives can't have 0 in the list. So every term here, xi, has to be greater than 0. For I equals 1, 2, and so on. Okay? So x1 has to be greater than 0, x2 has to be greater than 0, and xr has to be greater than 0, and everything in between. For counting the number of distinct positive integer valued vectors. And this is how you do it. Where did that number come from? I'll actually put a link in the description of where it comes from. Talking about it in this video I think it'll just waste time. It's not that interesting. Just know that that is the number of distinct positive integer value vectors. And you all know how to solve this, right? When you have an n, you have an r, you know how to solve and choose r. And it's kind of weird that this comes up in counting the number of vectors, or the number of values that satisfy this equation. Okay. Proposition 2 is actually the one we kind of care more about because we like to include 0. Because, well, 0 just makes everything better, I think. So proposition 2 says there are, I'm running that way too close to the top. Sorry about that. Proposition 2 there are n plus r minus 1, choose r minus 1, distinct non-negative now we're talking about non-negative, so it includes 0, the list includes 0, non-negative integer value vectors x1, x2, xr, right? This is just the list of numbers that satisfy the equation, which is the same equation. But remember, this is just the list, don't get scared. And what this is counting is the number of lists like this that will satisfy this equation. So this list that satisfying the following equation. So it's the same equation, right? So all the values from your list added together has to equal some number n. In the first example is 3. But this time, every term in our sum can be 0, so greater or equal to 0. For I equals 1, 2, and so on. So now every term can be greater or equal to 0, right? Because we're talking about non-negative. In this case, here was positive. So when you're talking about non-negative, this is the number of vectors that you come up with that satisfy this equation. So again, this counts the number of lists that include the values here that will actually equal your n. And each term here has to be greater or equal to 0, and it has to be a non-negative integer. Remember, so you can't have 4/5 square root of 2. It has to be an integer, and in this case, non-negative. Here it has to be positive. And that's it. This is how you count for positive, and this is how you count for non-negative. So let's just refer back to the last example when we had x1 plus x2 equals 3. And let's talk about non-negative, okay? Let's not talk about positive. So as you saw before, we counted 4 vectors, right? 4 lists that satisfy this equation when x1 and x2 have to be greater or equal to 0 and be an integer. Well, let's use this. This says that if you use this, it'll actually just count that for you. So we should get 4 if we use that. Well, what is our n? Well, our n is 3, right? Our n is 3 here. What is our r? Well, if you notice, r is your last number of terms. your last number of terms here is 2, right? So your last term here 2. R is always the last term. So R equals 2 in this case. And that's all we need, right? Here you just have a -1. You just need the n and the r. And it says to count the total number of lists or vectors that satisfy this equation for non-negative integer value vectors is just n plus r minus 1. Choose r minus 1. Where in this case, n is 3 and r is 2. So 3 plus 2 minus 1. Choose r minus 1. So 2 minus 1. 3 plus 2 is 5, minus 1 is 4. 2 minus 1 is 1, so you have 4, choose 1. If you remember back to the properties of combinations or multinomial coefficients, 4, n choose 1 is just n. 4 choose 1 is 4, and you can just calculate that in your calculator. And yeah, we did have 4 vectors, right? We had the 3, 0, 0, 3, 1, 2, and 2, 1. Those were the number of lists that satisfy this equation. And this actually just counted it. Yeah, we don't have them listed, which may be useful in some cases, but for us, we just want to know how many there are, and we know that there are 4, which is good. Okay, so now we covered this, and we'll just do, I think, one example. It's a 2-part example, and one more definition, and then an example of that, and then we're done with combinatorial analysis. Okay, so let's do that example right now. Okay, so let's do an example that actually utilizes the propositions, and specifically we'll be using proposition 2 because we care about that one a lot more than the first one. So this is a good example if you like finance or economics or whatever, because that the problem involves investments and strategies for investments. So I encourage you to try this example on your own. It has 2 parts to it. Just a hint, it utilizes everything we just learned about the number of ways to count integer solutions to an equation. So let's go through the example. An investor has $20,000 to invest among 4 possible investments. So he could put any amount he wants within each investment. Each investment must be in units of $1,000. If the total $20,000 is to be invested, how many different investment strategies are possible? Well, first let's denote the investment strategies, okay? And another word for investment strategies are just groups, right? Because one group is the first investment strategy, the second is the other one. So let the list x1, x2, x3, x4, or the vector denote his possible strategies. And what we want from this, well, we want the sum of the amount in each investment to equal $20,000 because he has to use all of the 20,000. And notice how I'm writing 20 and not 20,000 because each investment is in units of $1,000, so it will work itself out towards the end. So you write 20 instead of 20,000 because each investment must be in units of $1,000. So the unit here is 1,000, 1,000, 1,000, 1,000, and the unit here is 1,000. Now, why do we use proposition 2 instead of proposition 1? Well, because in the real world, he could put in $0 into investment 1 if he chooses to, right? He doesn't, that's allowable. So, because the list can contain the number 0, we have to use proposition 2 to count the number of total investment strategies here. Okay. Proposition 2 says there has to be n plus r minus 1 choose r minus 1 different strategies. Well, first we have to denote our n and our r, right? That's always the first step. Our n and our r. Okay. Oh, and also for here, so if you want to just denote for yourself that each investment strategy can be greater or equal to 0, you just denote it as such. Okay. And for I equals 1, 2, 3, and 4. Okay. Well, what is our n? N is always the last thing in the equation, right? It's the thing you're trying to get to. So n is 20. If you look back at your notes when you're summing and you have an n here, that's your n. And r is the number of groups that you have. In this case, 1, 2, and 3, and 4. So 4 groups. And that's actually all you need, right? You just need an n and an r, and you have everything filled out. So let's fill out the missing variables. N is 20 plus r, which is 4. And I subtract the 1. And then I choose r minus 1, which is 4 minus 1. So this ends up being 23, choose 3. And that comes out to 1,771 total different investment strategies. So this is the possible strategies. Possible strategies. So each xi here denotes the amount he's willing to put in. So he could put in 0 or he could put in more. It doesn't matter. We just know that there's this many possible vectors, this many possible strategies, this many possible lists of the numbers x1, x2, x3, x4 that satisfy this following equation, for which xi has to be greater or equal to 0 for I equals 1, 2, 3, and 4. That's all it is. And if you got to this, good job. And if you didn't, it's fine. You know, if you couldn't get to this either because you didn't understand that you had to use non-negative instead of positive, or maybe just there's some algebra mistake, just look back and see where you went wrong and leave down a comment and we'll get through it. Okay, and part B for this question says, what if not all the money need be invested? So he doesn't have to put in any money. He doesn't have to put in the whole $20,000 into his investments. He could leave aside some money. So for example, you know, so this means, the question is saying that this means he leaves some money aside from the 20,000. Some money aside. And let's say, I don't know, he leaves it in a safe. For example, i.e. in his safe. Well, if he leaves some money aside, that's an amount, right? It's the size of money. And he leaves it in his safe. Well, let x5 denote this amount of money, right? Because we need somewhere to put it. Well, that money just doesn't disappear. It has a value. So this amount is left aside, but this amount plus all of these still have to equal $20,000. So what we have now is a new equation where this was the one before, but now he's not putting in the whole 20,000 into these investment strategies. He's leaving some in reserve. He's leaving some aside in his safe, but they still have to all add up to $20,000, correct? Because money just doesn't disappear if he's just leaving it aside. He didn't spend it yet. So remember, I'm writing 20 here because each of these represent, it's a unit of $1,000. Okay. And well, we still can choose 0 for any of these, right? So we're still dealing with proposition 2. So we still have n plus r minus 1, choose r minus 1. Now let's fill out the gaps again. N is still 20 plus, well, r is actually 5 now because we have 5 different groups, right? The first 4 represent our investments, and the fifth one represents the money in his safe. So r equals 5, and we always subtract the 1 there, and then 5 minus 1 on the bottom. This equals 24, choose 4, and you just punch that into your calculator, and you should get 10,626 possible strategies. And notice the escalation from 1,771 to 10,000 right when you add another group, another place to put in your money. Something to think about. Okay, so that actually dealt with the number of integer solutions to equations. And if you're thinking, wait, so what was this all for? Okay, we did use some combination techniques here, but I still don't understand why we did it. In this next section, it's a small section really, but it does come in handy, and we kind of needed this to count the number of vectors needed, and you'll see why soon. So let me erase everything. So it's our last topic for this whole chapter. We finally did it. And remember, next video we'll be doing a bunch of examples on section 1. So everything from counting to permutations to combinations to everything we learned today. We'll be doing a bunch of examples. And yeah, that will cover section 1, and then we can finally move on to actual probability. Okay. So this section is called the Multinomial Theorem. The Multinomial Theorem. And if you already guessed, this is just an extension of the Binomial Theorem, where the Multinomial Theorem, instead of utilizing the binomial coefficients, remember the binomial coefficients is just n, choose r, the Multinomial Theorem utilizes multinomial coefficients. Multinomial coefficients. So hence the name of the theorem. Which are not that. This is binomial. Multinomial coefficients, if you remember, is n choose n1 comma n2 comma all the way to your last r group. So it utilizes this into its theorem, and this is how it looks. If you have a sum of numbers, x1 plus x2 plus all the way until xr, so you have r amount of numbers, and it's raised to the power n. Well, using multinomial coefficients, this can be regarded as the sum over the vector or the list of n1 to nr, such that the sum of this equals n. Right, we saw that right before. These have to equal n. So what is this saying? The sum is over all the lists that are possible, such that the sum of each individual number here in the list has to equal n. And you're taking the sum of n1 comma n2 comma nr and choose all of that. So that is your multinomial coefficient right there. And then you're multiplying by x1 to the n1 power times x2 to the n2 power times all the way until you reach your last xr and to the nr power. So remember, you always have the same number of x's as you have n's, and that's how it's always going to be. And we'll see one example of an expansion. These problems using the multinomial theorem is actually very tedious. It's not hard, it's just a lot of work. So I'm going to give you a very simple example, which will still take a little more time than I would like, but still, it's worth going through. Because it utilizes everything we just did. So if I don't do this, then the section we just did about counting the number of integer solutions will seem pointless. Okay, so here's our example. We want to expand. So remember, what I'm going to be doing right now is a very simple example that you could do using the FOIL method, obviously. But I just want to utilize this so we can get a nice feel for it. So I want you to expand the sum of x1 plus x2 plus x3 to the second power. And you have to use this. You can't FOIL it. You can, but try to use this first. So how do you even go about this problem? Because when we use the binomial theorem, we don't have to think about lists or vectors, right? I mean, this is kind of abstract and it looks weird. So it might look scary right now, but I'll tell you what to do with using the multinomial theorem right now. So here's what I can give you as a hint. First, find all the possible non-negative, right, proposition 2, non-negative integer valued vectors, which are this list, n1, n2, comma, all the way to your last one. So that is your list. So you have to find the number of lists that satisfy such that the sum of this equals n. Right? That's what we did in the previous section right before this. So you guys already know how to find the number of lists like this because we did it before. And the reason we do this is so we know how many multinomial coefficients we have, right? Because if you notice, the bottom here is this list, right? The bottom is this list, and we'll have more than one list because in the last section we saw we had 1,771 lists. So, in this case we won't, but we'll have more than one and then we'll have to sum over those different multinomial coefficients. And if that's still confusing, don't worry, once we get through it, you'll see what I'm talking about. So we know how many multinomial coefficients there are. Okay. So we want to find the number of non-negative integer valued vectors such that the sum of this will equal n, and that way we'll actually know how many multinomial coefficients we get. Well, how do we count non-negative integer valued vectors? Oh, proposition 2 tells us there's this many, right? N plus r minus 1, choose r minus 1. Great. Now in this example, right, we have to find our n and we have to find our r. Remember, n is your exponent. Oh, your exponent here is 2. So n equals 2. And then r is the number of groups you have, right? It's always this last number, right? Because you see the r, they always match. And it's always the number of groups. 1, 2, 3 groups. So r equals 3. And that's all we need to count the number of different vectors, the number of different lists of these numbers. So we have 2 plus 3 minus 1. Choose 3 minus 1. That's just 4 choose 2, I think. 4 choose 2. Yeah, so 4 choose 2, do it in your calculator or use the factorial definition, and you should get 6. 6 what? 6 possible vectors, 6 possible lists, but that also means you will have 6 possible multinomial coefficients because the list is already built in the multinomial coefficient, right? The list is right here. It's the same list, it's just over there. So we'll have 6 multinomial coefficients. Multinomial coefficients. And now that we know how many we have, this is where we actually start trial and error, kind of. We have to actually list them out. Because this actually tells us how many we have, it won't be too hard to find out what each N1, N2, and N3 is. So our next step is find the 6 vectors. Find the 6 vectors. Remember, 6 vectors is this. This is a vector, or 6 lists, right? 6 lists, such that the sum of N1 plus N2 plus N3 equals N, which is 2. Why do we only have 3 N's? I mean N1, N2, N3? Because we have 3 groups. And as I told you before, we always have the same number of N1s, N2s, and R's as we have X's. So in this case, we have 3 groups. So you'll always have 3 here. And those 3 have to add up to 2. Okay, so we know we have to have 6. So let's try to find our first one. And remember, each N1, N2, and N3 could be greater or equal to 0. And they have to be integers. Okay, so what can I pick for N1 first? Well, let me pick 0. And let me pick 0 for N2 as well, right? The first term here, it represents N1. The second term represents N2. That means if N1 is 0 and N2 is 0, that must mean N3 has to be 2. And I found my first vector, right? This is the list of N1, N2, N3. Okay, that's 1. I need 5 more. Well, I could pick 0 again for N1, but then I could pick 2 for N2 and then 0 for N3. Oh, but then I could switch the 0 and 2 here for N1, so I pick 2 for N1, 0 for N2, and 0 for N3, right? Because 2 plus 0 gives you the 2. Okay, so now we're half done. We have 3 more. See, so why did we do the last section? Because now we know how many we should have. And if you don't, it's kind of hard to sort of see how much you need ahead of time. So I like first finding how many vectors I should have, and then actually apply this theorem. Okay, so we did half. We need 3 more. What else can we come up with? Well, I know 1 plus 1 is 2, but we have 3 terms. We'll just make one of them 0, right? So let me pick 1 for N1, 1 for N2, and then 0 for N3. And then just switch those numbers around, right? You're allowed to do that because they're different lists. 1 for N1, 0 for N2, and then 1 for N3. And then finally, 0, 0, 1. And we're done. We found our 6 lists. That's it. That's all it took. But we're not done, right? Because now all these lists will apply to this, and then we have to sum over all those different lists. Okay. So now that we've found our list, let me erase this, and we'll get to that, and then we'll be done. Okay, so x1 plus x2 plus x3 to the second power, and we'll be expanding it using this. So, what does it equal? Well, first we have to sum over the first list. So let's do this first. Where n1 equals 0, n2 equals 0, and n3 equals 2. Okay, so n choose, well, what is our n? N is 2, right? It always stays the same. And n1 is 0, n2 is 0, and n3 is 2. And then you have to multiply x1 to the n1 power, x2 to the n2 power, and then x3 to the second power. And that finishes the first term, right? Because we did our first list. Great. So we're done with our first list. And notice how it was utilized in the multinomial coefficient on the bottom and in the exponents. But we have to sum over the other lists now. Okay, so I still have my same n, right? It's always 2. But now I'm going to be summing over this new list, or this new vector, where n1 equals 0, n2 equals 2, and n3 equals 0. And then you have to multiply by x1 to the n1 power, which is 0, x2 to the n2 power, which is 2, and then times x3 to the 0th power. Plus the new multinomial coefficient that utilizes this list. So let me erase this one. As you can see, this will be a big expansion. That's why I only picked it to the second power. Otherwise, it would be a total mess. You could do it. It would just be crazy long. We might do a problem in the next video that will be extremely long, which I'll see if I'll put it in. Okay, so our next multinomial coefficient will be 2, choose 2, 0, and 0. Put it too far. And then x1 to the second power, x2 to the 0, and x3 to the 0, plus this one for our multinomial coefficient. So I'm going to put the plus there, and I'm going to continue it here. So n is always 2, and I'm choosing 1, 1, and 0. 1, comma, 1, comma, 0 times x1 to the first, x2 to the first, and x3 to the 0, plus that new vector list. So plus 2 choose 1, 0, 1. 1, 0, 1 times x1 to the first, x2 to the 0, and x3 to the first. And then finally, wow, our last vector, the sixth vector, is to choose 0, 0, 1. 0, 0, 1, x1 to the 0, right, because n1 is 0, x2 to the 0, and x3 to the 1. And we're done. We used all the vectors. And notice something. When we counted the number of vectors, we also counted at the same time the number of multinomial coefficients, which was 6. Notice you have 1 multinomial coefficient, 2, 3, 4, 5, 6. And that should make sense because you're summing over all these vectors, and we had 6 of them that I just erased. Okay, so working through this yourself, counting this up and just, solving for the 0, 0, and the 2's and stuff, what you'll end up getting after all of this is x1 squared plus x2 squared plus x3 squared plus 2x1 times x2 plus 2x1 x3 plus 2x2 and x3. That's what you get after doing all that work. When you could have used the FOIL method, maybe it would have been easier. But I think this is more fun because we used everything we just learned. And it looks pretty. So that's that. And that concludes combinatorial analysis, which was section 1. So we finished section 1 or chapter 1. And next video we'll be doing a bunch of examples on the basic principle of counting, the general version of it, permutations, combinations, binomial theorem using the multinomial theorem maybe once, and again everything we learned. We'll be doing maybe 15 examples, and after that we'll finally be diving in chapter 2, which deals with probability, which still uses everything from combinatorial analysis. So don't forget anything here. It's very important. Especially the examples we do in the next video, they'll be more tricky than some of the examples we did in the videos. Of course, I'll work from easy to hard. The reason I want to do the tricky ones last is because I want you guys to really fully understand this section before we move on. Otherwise, doing the probability is going to get tough. And if you don't know this, then there's no point of moving on. So make sure you really fully grasp everything we did in the first 3 videos. Well, the lessons for sure. So I'll see you guys next time. I hope you enjoyed the content. Please leave down suggestions. Maybe I've been wanting to do shorter videos, but I want to go in depth, and I've been trying to shorten the videos by skipping me writing the examples. So I think that's as far as I'll go. I don't care if the videos are long, as long as you guys learn. So that's all. See you guys in the next video. Bye.